Thank you for the long wait and patience. We are going to start the special seminar we are hosting. Mandela Bright Quashie from the Michigan State University. And today he's going to talk about exciting topic, which is smarter particles for smarter plasma simulations. So the stage is yours.
Thank you very much, and thank you all again for waiting. So as Doug just said, presenting on this moment enhanced particle in cell framework, which we are busy calling smarter particles for smarter plasma simulations. This work is a joint collaborative efforts between my advisor and the Grizzly, also of Michigan State University, Josh Gabriel of UT Austin, Chitan of Georgia Institute. We are being funded by Los Alamos, National Science Foundation, Chamlet, and also Michigan State University. So today, this is the plan for my talk today. I'm sure we have diverse audience, so we'll talk a little bit about plasma, talk about modeling and then particle itself. Then a method that was developed by Dennis Hewitt of blessed memory will try to do something about what we have done. And we see how we improved it using Scovel Weinstein approach, a paper that we wrote in 1994. We built upon it to develop this model. Before we do that, we'll look at some preliminaries, then we'll look at some applications, and then also talk about some applying to numerical methods, and then some proposal. So as most of the members in this audience will know, plasma is an ionized gas. As we heat it from solid, it becomes liquid. From liquid, it becomes gas. And as the temperature decreases, this will happen. And it's used in, basically, it's about 99% of the physical earth and physical environment is made up of plasma. We use it for medical sterilization in TVs, plasma TVs, and fusion energy. So in our quest of we getting clean energy, that's why we're also studying plasma. I'm sure soon we'll be able to get the answer that we have been looking for all these years. So why then? Because plasma is important, we need to model. We want to model it, and we'll look at this simple analogy here. If we want to model n particles and we want to loop over them, that is computing the Coulomb force. We have this equation that we see here, and then if we want to calculate the electric field, that means we are doing it for all the particles. So that means you will be able to loop over n-1 particles, and that means that we require n-1 force evaluations per particles, and that means that the total cost will be about n squared calculations. And clearly you realize that as n increases, it's going to be very, very particle. So we want to find ways or means to be able to compute these things, get accurate answers, but also being efficient. Let's elaborate it further. So let's assume we have n, which is 10 raised to the power 16 particles. Here we are looking, this is at least the bare minimum that we are even going to, which is 10 raised to the power 16 particles in 1 meter vacuum pressure. And then also, if we decide that, based on a simple calculation, realize that the Coulomb interaction take about 10 minus 8 seconds to compute. Hence, the total interactions, which we just looked at, the n-1, we end up having 5 times 10 raised to the power 10 raised to the power 31 in total interactions. And using the 10 raised to the power negative 8, realize that approximately it will take us 1.6 times 10 raised to the power 16 years to do that computing if we want to do that. And using the machine, the ASAT November, the most powerful machine, which is here plus Liverpool. When we do these calculations, the performance is 1.742 exaflops. And if we assume 100 flops per interaction, that means we end up having about 910,000 years to do the same calculations. So even though the total time here is a lot, we end up having 9 910, almost a billion years to able to compute this. So realize that hence we need faster methods like particle and cell to do plasma simulations. And one of the key equations that is able to govern plasma simulations well is the Vlasov Poisson. And then in terms of Vlasov Poisson, we have these three basically equations. The F is just talking about the distribution function, which is made up of the position and then the momentum. And then the phi is the basically the potential. Then this is the Vlasov equation. This particular one, the middle one, is the Vlasov equation. And then this is the well-known Poisson equation. So together they become the Vlasov-Poisson equation. Now here the fields are self-consistently determined by F. So everything here is self-consistent. Okay, we don't have a prescribed potential here. Now, what then is the particle itself? What we are trying to make better? It's basically a numerical technique that combines the particle-based method and the grid-based methods together to get this. I'll use this picture to elaborate it further. So basically, earlier when we saw the n particles, we are going to have them to cluster together to form something like the superparticles or macroparticles. So the macroparticles will represent a group of real particles, which automatically will reduce the computational load. So this is what we have as equation 1. So the idea here is this. You have these particles, then you put them on a grid. So these particles, then that's what we have as our PIC. So if we have about 1 million particles here, we're able to reduce the number of particles to a little less than 1 million, or sometimes significantly lower. That's what we're able to see as the one as PIC here. So this is the idea of PIC. So from here, we're able to solve. We'll look at the algorithm shortly for you to see how it goes. So this is the algorithm for PIC. What you do is that you initialize the particles. Here, the standard one we use was the momentum and then the position. You deposit the charge on the mesh. That's what we just saw in the previous picture. Then we solve the electric field on the mesh. Then we interpolate the electric field onto the particles. Then we advance the particles using the information that we have got, and the cycle keeps continuing. So when we use PIC, we want to see why PIC is better than doing it as a direct method as we just saw. When we assume m equals 10 to the power 9 breakpoints, we realize that the complexity will reduce to just 10 to the power 16 operations. And if the flops is 10 to the power 18, running on the same El Capitan, we realize that something that was close to 1 million will now just be a sub-second computation. Very fast. So you realize that PIC at the end is able to help us model plasma better, at least without a lot of computational cost. But clearly, we know that PIC will always have problems. Any model will have problems. That's my advisor keeps saying. All models are not perfect. Some are better than the others. So we want to see how we can improve this model. And these are the main problems that we saw with PIC. Physical and numerical. So they are noisy due to finite particle sampling. The energy is not really conserved, and also it struggles to resolve the fine scale velocity structures. Computationally, it's expensive in high dimensions. It also requires more time steps to be able to get stability. And then in terms of when you are trying to parallelize them, there's a problem with load imbalance. In terms of the algorithm itself, there's a problem with complex charge deposition and interpolation. Then it's also very difficult to handle collisions natively. And then also there's also a problem when you are dealing with multi-boundary conditions. Now you realize that there are some of them are color coded. Our method basically has been, the green ones are things that our method has been able to solve. So we have been able to solve the green ones, better the green ones. And then the yellow ones, at least we have an idea that it's working. And then the black ones are basically what we have not really come to terms with, or we have not been able to see any kind of improvement. You know, as we keep researching and then enhancing our method, maybe we'll be able to solve the other, either better the other black one. So basically, our has reduced noise, our preserves energy, our is able to resolve the fine scale velocity structures better than PIC. And then also in terms of the complex charge deposition, ours is able to look at it better or handle it better. In terms of computational, ours is not as expensive as PIC, and then ours is easily to parallelize as compared to PIC. So, what is smaller particle? We are not the first to think about smaller particles. Dennis Hillertz came up with his, and the reference that you can see down there, that is Dennis D.H. Hillert's fragmentation, merging and internal dynamics for PIC simulations with finite size particles. If you look at it, so all he did was, if you have the standard PIC, he's able, and then this is the normal particles, the real particles, and then these are our one super particles. This is what we have. This is what we know we just described. However, what he did was, he says, you could be able to rather have a macroparticle for the real particles, have a macroparticles with this particular representation, which he calls the CPK smooth particle, or in a way, a smart particle. So what happens is, if you have the PIC structure, which is the Q and P, he is able to decompose it into one, have a share S. The share S link the momentum and then the position together. He has a VP, that is the momentum weight. He's able to track that one. And then also a particle weight, which is the W naught, and then a spatial weight as well. And this is able to capture the fluid and the kinetic properties better. At least when he does that, this is what he's able to do. And then also he's able to track the internal dynamics using this particular equation. The paper is a very I encourage audience to be able to look at it. But when he did this, but the key thing here is that he's using, it only works for Gaussian functions. That's what's for. It also doesn't solve the Hamiltonian problems. It's not energy conserving. And this is one of the what we realized that, okay, can we make this thing better? And that's where so let's look at the limitations of the CPK method. One, it's rigid. As I said earlier, it only supports Gaussian particles. It ignores Hamiltonian completely. Hamiltonian is not preserved. And then anytime you want to handle anything in it, you need to manually adapt it. So it's kind of difficult. And then also in terms of diagnostics, you need to use stringers. And one key problem is that it cannot go beyond the second order movement. We'll talk about it later. So this is what Hillertz tried doing in 2003, but I realized that these are some of the limitations that they have. So again, we are not the first to think about that smaller particle. Someone or a couple of people have tried doing that already. So what we did was using an approach by Scovel, Weinstein. But to be able to understand it, I will look at a little preliminaries because it's based on linear algebra. Most of the stuff we are working with is based on linear algebra. So a little preliminaries. So first of all, look at the Poisson bracket structure. So basically, a Poisson bracket that you see here on a smooth manifold M is basically a bilinear map that maps this into that, which is defined on smooth functions, x, y, z, satisfying these four properties. One, anti-symmetry. It needs to, the bracket should satisfy anti-symmetry. It should be linear. That's if you have C1, C2, it should satisfy this equation. It should also follow what we call the Leibniz rule. More or less, it's basically something like an associativity. And then also, one important key thing is it needs to follow the Jacobi identity. So when you have any this bilinear map with these four properties, then we are calling it as a Poisson bracket. Now, one key thing is that the Vlasov Poisson system itself has something to do with the algebra. So we want to build from there. We'll start by looking at Hamiltonian structure. So we say that a system is Hamiltonian if when you find the derivative of when we find the derivative of f with that, with a Poisson bracket with this, if this thing holds, then the system is Hamiltonian for all f in this particular thing, where h also belongs to that. So when this thing holds, then the system is Hamiltonian. Again, realize that in the Hewitt method, it didn't satisfy the Hamiltonian. So we want to have a system that will present the Hamiltonian. So that's why we are looking at it carefully. So if we let our n this time be G star, here, more or less that, wow, I'll explain it soon. Well, if we let n be that, and then we define the Poisson bracket as what we are seeing here, this Poisson bracket, then the Hamiltonian functional will have this, and using the Poisson equation, we have issues with the cursor. So basically the Vlasov Poisson system, this is what it follows. This is the phase space, this is the Poisson bracket, this is the Hamiltonian functional with its Poisson equation. So with these two foundations, we are ready to see whether the Vlasov Poisson, how it deals with Lie algebra. Now, a Lie algebra, G, is a vector space over maybe R or complex numbers, which is equipped with the Lie bracket. This here, you realize that all the stuff that has to do with the Poisson brackets, the Poisson bracket structure, it's almost apart from the Leibniz. So you realize that it's bilinear, it's anti-symmetry, it follows the Jacobi identity. So you realize that anytime you have a Lie algebra, this properties must be what? Satisfied. Examples are matrices which is under a commutator, vector fields under Lie derivatives, and etc. So these are what Lie algebra is. Now we have the tools to be able to see why the Vlasov Poisson is a Lie Poisson system. Why is it a Lie Poisson system? If we have G, the Lie algebra of smooth functions on the phase space, and we have equipped with this particular bracket, then the axioms that we just saw, or the properties that we just saw, it being linear, anti-symmetry, and Jacobi identity, is satisfied. And the G star I talked about, that means that each dual space G star will be equipped, or it evolves under this particular Poisson bracket. And this is what we get to realize, that then the Lie Poisson structure underlying the Vlasov Poisson system. Hence, the Vlasov Poisson itself is Lie Poisson Wallace system. Yes. So the whole idea is, mostly you always want to find a closure, a Hamiltonian moment closure for some of these systems, but we can't. It's normally continuous, and then we can't deal with all of them computationally. So why a closure is Hamiltonian, provided these three things hold. One, a Poisson bracket exists, the Hamiltonian is defined, and the dynamics obey what we saw the definition for what? For the Hamiltonian. So the whole idea is, if you have this sequence, M, moment sequence, we want to find out, as K approaches infinity, will we be able to recover the Vlasov Poisson bracket? That's the goal here. This is what Hewitt method couldn't achieve, but this is what we want to see whether we can. So to do that, anytime we have a Lie algebra, we want to see whether we can approximate it. And that's what we have this question in. It says, is it possible to construct a Lie algebra that approximates G, whose dual captures a finite number of fluid moments? And the answer is yes, through algebraic reductions. So there are two main methods to be able to approximate Lie algebra, either quotient algebra or subalgebra. But in this case, the main idea here is that the quotient algebra fails, and then the subalgebra also fails. But what Scovel, Weinstein, the genius that they did was, they were able to find a way to merge the good parts of both the quotient algebra and then the subalgebra together. So that's what we're looking at in the next slide. So what is the quotient Lie algebra? Basically, if we have a Lie algebra ideal, a subspace I is an ideal if the bracket in I for all A in I and X in G. Basically, that's what an Lie algebra ideal is. And then the quotient algebra is formed. We form when you have the G and then this particular I, then we are having the quotient algebra. So just to make life easier for everyone, an example is that if let all G be all polynomials, so polynomials in X, so that is 1, X squared, X cubed, etc. And we decide to take I to be the polynomial division of X squared. So basically, then our G slash I will only be made up of 1 and X. Basically, every term above X will be cut off. So this will only retain constant and linear terms. And this is where it's a bit problematic. And why is it so? So let's take an example. If we take a function where we have QP in the constant terms and then AQP, PB plus the curve part, like the normal polynomial. And if we retain only Q and P, then the space is not closed under Poisson brackets. Why? You realize that this will hold, but any term that has to do with any Q squared, QP or more will keep appearing. They force inclusion of yet higher terms, which we don't want. The algebra does not hence will truncate. And this is the reason why quotient algebra often fails to support consistent moment quotients. So this is why quotient algebra doesn't really work. Then I talk about subalgebra. So a subalgebra, let's look at the definition of it. A subspace H, subset of G, is a subalgebra if when you take H1 and H2 in H, and we take the bracket of it, for all what H1 and H2, it's still in H. A typical example is the 3x3 matrices, the upper triangular 3x3 matrices. So when you take this, and then you realize that all the terms, that's why earlier I told you about the matrix under commutator, they are what? They algebra. So D here, subalgebra remain closed under the bracket region. Again, it's problematic here. Why? Let's take the function here, where we have C with C1 and up etc. And then we try pairing the dual here with this. Then the brackets producing terms of order P. Even though we only want these sequence, the bracket will produce P raised to the power 4 and beyond, which will automatically break the closure. So the space of polynomial functions of fixed degree are not basically subalgebras. So this is the reason why you can't just go ahead and then approximate this system just by subalgebra or by just quotient algebra. So what did Scovel, Weinstein, what did they do? They take the G and then split it into B and then S, where both B and S are subalgebra. But here is the trick. They find an ideal in what? In S. But this ideal is in S, but do not need to be an ideal in G. So this is how powerful, this is what their main paper is all about. This is how they were able to cure this problem of subalgebra and then quotient algebra by what they call hybridization. They try to hybridize the two methods. So how is it done? So let B be a Lie group that integrates B. The diagram that you see here. So this is our, if you see, so if you have this, what happens is you're able to map this using this map here to this. So this is again. Okay. So as I said here, we have B and then S. The whole idea again is the B, you have the G, and then the B and then the S. The B will be more or less controlling the motion, and then S will be controlling the shape. That's the whole idea. So the S, and in terms of the shape, that means the movement. Now, they came up this, when you look at the paper, I think I have a reference here, yes. So when you look at this, they're able to decompose this thing using this particular map, and then also decompose this using this particular map, and then end up getting the dual. That's the whole idea on this paper, and it's very, very powerful. The paper is a bit test. You need to have a little like a bit knowledge about classical mechanics and then Lie algebra and Lie theory, but it's a very good read. Yeah. So to make life easier, this is the whole idea. You apply a sub-algebra reduction using B. Then you apply a quotient reduction using the ideal I in S. Then when you do that, you're able to combine both reduction via a direct sum structure, which embed the result in the original Lie Poisson space, and also this time around will preserve the Poisson bracket structure, and hence the Hamiltonian will then be preserved. So this is the reference to the paper, this 1994 paper. It's a very good idea. So again, let's see why it will work this time around. So if you have the Lie algebra B, the subalgebra encoding the symmetries, and then S, the complementary subalgebra, which has to be the linear in P functions. Then the I in the S here is the idea imposing the closure conditions. So if you want to find the moment closure, basically the zeroth moment will have the density, and then the first moment, which will be the S, will have the what? Momentum. And this hybrid reduction, that is the subalgebra plus the quotient algebra, will end up supporting the Hamiltonian closure. So to get this whole thing done, the most important thing here is what is the map, and this is what we call the smart particles. The idea is you start with two particles, a particle with only two information, Q and P, but you end up having this delta functions here using the method that we have talked about. If we look at it in our paper, currently we are working on publishing it soon. So I'm hoping at least I'll give it to Dr. for him to make it available to anyone who wants to get it read. So when you do that, you end up having this, as you can see here. The interpretation here is simple. It combines particle data and the truncated moment to represent the F within the dual space. And that's why we call it a smart particle. What happens? Basically, you start with only two informations, Q and P, but you then have more information attached to it. So normally we are starting with only two information, they end up having 6 informations. And that's why we are calling it smaller particle, because the information that has, you have more information to deal with the system. So automatically, in getting this map, it comes with its own, it's more or less, there's an induced Poisson bracket that comes with it. And when you look at it carefully, you realize that the first aspect of the Poisson bracket before the summation has to do with the standard Poisson brackets for the normal Vlasov-Poisson equation. And then the additional aspect has to do with the S, the moment aspect of it. So this bracket is induced, as I said earlier, by the Poisson map, and that supports moment-based Hamiltonian system. You can also look at one of the papers from one of our collaborator, J.W. Berry. He also handled this in terms of variable moment fluid closures. Okay, so with what we have seen the theory behind all that we have done, we want to see how we will be able to bring it into a numerical results. So I'll try to make it a bit easy for people to follow. So basically, we start with the standard PIC particle. This is standard PIC. Now these particles now exist. Let's assume we have about 100. Then we decide to cluster these particles. So when we cluster these particles, by finding the mean, here we use the k-means algorithm as our starter. So we end up having this new, more or less the weights, new Q's and new P's, and these are the averages. Then we then find the deviations of this, the deviations, the first order deviations, using Taylor approximation. So that's what we did here. So then each particle will end up becoming sparse. So basically that's what we have here. The last bit of it here. So we started with only QP. Now we have Q, P, Q star, P star, and then South star. To the best of our knowledge, we are the first to be able to handle this, to be able to get a particular kind of result that we are showing you today. So basically our standard PIC now becomes this new PIC. So it's now this particular one. The new F becomes this. This is what we are calling the smart particle here. Then it comes with its own Poisson brackets, and that's what we see here. And when you have these two, then you are basically ready to solve the system. We have what we call the reduced Hamiltonian or the collective Hamiltonian, which is the pullback because the original Hamiltonian will not work. The original one will break. And then based on new variables that we have, we end up having this particular variables, the new variables. Instead of Q and P now, we now have these 6 variables using symbolic, we believe, from able to solve this problem. So we have seen all the method, we have seen how we think it will work. I want to see whether it will work in real life. So let's start with a prescribed potential, a very simple toy example. So this is original. Here we have in our standard PIC particle, original particles. So they are 6 up here, 6 down here. Then we cluster them, that is, we pair them here. And then we also have superparticles here. So this, I can't say for sure that these two are what is here.
For the inconvenience, we will sort this out. Awesome.
Okay, so let me rewind. So let's see. Okay, so we are going to solve a toy example to make sure what we have done works. To start, we want to see how we can compare it with the standard PIC particle. And in standard PIC particle, that means L here, this L, when L should be either 0 or 1. So that's what we have here. The SK is 0, E is 1, and then we are using the prescribed potential of sign Q. So what we do here is, as I explained earlier, so as I said, I'm starting again. We begin with 12 PIC particles. So that's what we have here. 6 up there, 6 down there. Then we use K-means cluster to bring them together. And I was saying earlier that I can't say for sure that it's these two particles that come here, that will combine to form this. The reason is that it needs to account for both the position and then the momentum to be able to know which one is too close to bring them together. But likelihood, it's possible that it's these two that is that is coming to the side. And then these two will come to this, and then these two come to that. At least let's see that one. And then the same applies to the one in red. So here, the original 12 particles have been reduced to just 6 particles. We want to see, will it matter? And the answer, we now get a new Hamiltonian. That is the prescribed potential. We get a new Hamiltonian here. Then that's the Vlasov Hamiltonian. This is the distribution function. We want it to compare it to the standard PIC particle. And then this is the collective Hamiltonian. This is how it will evolve. And then using this particular Poisson bracket, you end up having these systems of equation. So this is where our method more or less is a bit of a disadvantage. Because in the standard PIC particles, you only solve for Q and then P. But in our method, we are solving for Q, P, the big side, the Q star, and then the P star, and then the small star, the canonical variables. But if you look at the equations carefully, you realize that the psi basically are not really coupled, or they are not coupled with the other 4 variables. The big star is just this, and then the small star, the psi star, is just a constant. So this was, so I'll talk about it later. I just wanted you to note this. So in a nutshell, basically, in as much as we are solving 6, we might basically be solving only 4 variables here. So with this, after time t equal to 15, this is how the movement goes. And then in SW-PIC, this is what we now see. We want to see, so this is how the variables, the new variables works. So this is just for only 1. Remember, they were 12 reduced to 6. So we just pick the 0th one, and then this is how it evolves over time. The Q, this is how it's evolving. The P, this is how it's evolving. The psi keeps evolving this way. And then the psi star, it's kind of small, but this is how it evolves. It looks like it's bounded. The P star, also very small, and it's descending. And then as we know, the psi star is what? It's a constant. Originally it was 1, and then since it's now 2, based on the formula that we saw earlier. That's why you're seeing 2.0. Now, not all the 12 will not act the same way. All the 6 will not act the same way. I'm just using this as an example for you to see that all of them evolve differently. Yes. So now we want to see whether our system is working. So we want to find the Hamiltonian evolution. So when you look at the Hamiltonian evolution, you realize that our SW-PIC, that is the blue one, and then the standard PIC, that is the orange one. And when you look at the table that you see here, in a nutshell, the SW-PIC has 36 variables, and then the standard PIC, because it's 6 times 6, making it 36. And the standard PIC has 24 variables. That is 2 times 12, that's 24. And then in terms of drift, SW-PIC outperforms standard PIC. The root in RMS drift also, SW-PIC is better than standard PIC. And in terms of the noise as well, SW-PIC is better than standard PIC. So we realize that our method, the toy example that we have, is working. Again, you have a group of particles, you reduce them or cluster them, and then get the information to make them smarter. Then we use that to evolve, and then find the systems of equation in terms of this new set of variables. And then that's what we are seeing, the Hamiltonian being preserved here. There's a bit of deviations because we are clustering them, it will not be lying exactly on they will not be lying exactly on each other. Okay, so now that it's working, we want to now apply it to a normal problem, a standard problem, a 1v1 electrostatic PIC. So this is Vlasov Poisson equation. Again, we are still using SK equal to 0. So this is what we have. And this time around, we used finite element method to be able to solve this problem. Why? Because the FEM method automatically comes with its own shape functions, which will be basically be in sync with our method. It's able to handle delta functions naturally. And then the variational problem itself or formulation normally supports periodic boundary conditions. And that's the reason why we stick to FEM. We are trying to see in our next work, we will try to apply to Fourier. We also try to use other methods, maybe finite volume and etc. to solve it. But for now, in our first problem, this is what we try to do. So we have the problem, and we got the weak formulation, we got the matrices, the stiffness matrix, and then the vector that is using the density, charge density, to be able to get this side. Now, one key thing is you realize now we are dealing with a lot of equations. So you need to keep track of the derivatives in terms of Q and then the P. And this is one of them. I just wanted you to see how it evolves, because in the collective Hamiltonian, the structure, I didn't present the structure visible. So you have your F, and when you find the derivative of it, you need to keep track of it. So it looks like what we are having here. So now that we have the system, our K, our F, we know the collective Hamiltonian here and everything, we go ahead and find our discrete Hamiltonian. This is what we have as our discrete Hamiltonian. Now realize that it comes with some of the canonical variables as you see here. Then using the discrete Hamiltonian and also the Poisson brackets that we saw earlier, we end up having these evolution equations. And again, if you look at it carefully, you realize that this side, the two sides, mimic the two example that we saw. It's still constant, and then these values are basically what you saw earlier. And then this four also are the same, 1 over MPK, and then so by just using your eye to check, realize that the prescribed potential has some kind of similarities with the self-consistent one. Now, only Q, PK, Q star, PK star evolves. The rest are not. Psi K is a constant and big psi is auxiliary. So now that we have this setup, use the K-means algorithm, get our P star and everything, we now apply it to two-stream instability to see how it performs. So basically, in terms of two-stream instability, it's a well-known problem in kinetic simulations where you have two counter beams coming, maybe a blue and then a red, and then with time you want to see the instability of the form. So we compare our standard pick with our SW, with the SW pick over time. So when you look at it, originally they started with being deviated, just like the two examples. All the red were up, all the blue were up. At time t equal to 25, you end up seeing this. At time t equal to 50, you end up seeing that. And at time t equal to 75, you end up seeing this. So realize that in as much as automatically we know that it will not lie, they will not lie on each other because here we are compressing them. But realize that the instability is forming, the phase space looks like it's matching. Okay, now if it's working, let's see the growth rate of them. Realize that both the peak and then the SW peak, both of them follows the theoretical growth value. So we end up having this. So what are we seeing? Realize that, and this particles here, the standard peak is using 100,000 particles, and the SW peak is using just 20,000 particles. So we're able to use lesser particles to be able to compute to get the same result that would have used 100,000 particles to get. Okay, and then we are getting the growth rate also similar. We didn't stop there. Okay, if it's working for two stream, we only work for London damping. So we did London damping as well, where a wave is moving, and then as energy is more or less stolen from it, this is what happens. The initial condition is basically what you can see here. So we did that again, and this is the result. The standard peak is using 100,000 particles, and then the SW peak is using only 20,000 particles. So when you look at this, you realize that it follows the same thing. Then, in terms of the decay rate, it follows the blue one is for peak, and then the green one is for SW peak. Here we try to bombard, add so many particles. So here we are comparing this result with a continuum code. So that's what we did here. We compare the result with the continuum code. We are using the continuum code as the truth, our ground truth or the true solution. So when we compare everything, I want to look at the error scale. So here we want to see how that the 100,000 particles and 10,000 particles, how do they perform? So when you look at the standard peak, using just with 1% relative error, which is the red one here, realize that to get that, you need, with 20,000 particles, you're able to get 1% relative error. But you need about 80,000 particles to do the same thing for SW, for standard peak. So in terms of our error, you see clearly, which means that our method is reducing the noise. As if the noise is being reduced. It's more or less in terms of how the Monte Carlo sampling is done. Our method is what outperforming it. Again, when you look at, you plot the log on a log scale, you realize that the SW peak is outperforming the standard peak. And the deviations, as you can see, because it's the same thing. What we saw earlier is what we are putting it on a log scale. The same result, this is for two-stream instability. We got a similar result for land on that pen as well. Now, one key thing we didn't look at earlier before, but at the end of our work, we realized that there's another advantage, and that's what I keep saying that. So let me explain it here. So SWP achieved 1% error with just 20,000 particles. The standard PIC needs about 100,000 particles to get into the same thing. What has happened is that we have been able to reduce the particles by 5 times in terms of particle count. Then, when you look at the table, and when you are using just using maybe 8 bytes, standard PIC for 100,000 particles, you have 2 variables. The degrees of freedom basically is 200,000. So the memory here, you need 1.53 to do the same thing. 1.5. Now, when you use SWPIC, we'll have 6 variables. We are using the normal one because we saw 6 variables, we are using it. So, and we are having 20,000 particles. So we end up having 120,000 particles, which is about 0.92. So basically, we have been able to, our method is saving memory as compared to the standard PIC, even if we use our full SWPIC. Now, if we decide to ignore the size star, when we ignore that one because we know it's a constant, then we have what we call optimized SWPIC, and that means we'll save about 50% of space. And then when we ignore both the psi and then the psi k, where we are calling the minimal PIC, you end up saving about 60% of memory here. So basically, this one we didn't look at it this earlier, but we realized that it's a very important advantage that we are having as the work was progressed. So tracking only 4 variables will reduce the memory storage by 60% compared to what? To the standard PIC. And that's one advantage that we saw. So basically, this is what we have realized. One, in this method, Hamiltonian structure is preserved. It's less noisy. Computationally, we're able to save memory as compared to standard PIC. And then all that in terms of the algorithm itself, ours is in terms of the position and then interpolation, our method is what is also way better than the standard PIC. In terms of what we want to do next, I propose or what we want to continue from here. One, instead of we just ignoring the moment aspect, we now want to add the moment aspects to it. Because in as much as the first one is the 0th moment, we want to increase it to what? To other moments. That's one thing that we want to do. And then the goal here is to move it to GPU and then use Cocos and Cabana to go to do proper more or less advanced SQL computing to get these things done. And then also we use K-means algorithm here. We want to try other kind of clustering algorithm that will make the method a bit faster. Because we know that in as much as we are getting 20,000, 5 times reduction, we might even do better than that. Yes. So basically, this is what we have. We're able to build a structure preserving model via the Scovel Weinstein reduction. That's what we are calling the SWPIC. We represented the particles using delta functions and their derivatives. And then we were able to extend the PIC with higher order moments and then geometric structures. Our key result is that we recovered PIC as a special case. We were able to capture the shape variables by this moment, and then we were able to reduce the phase space noise. There is low memory usage, and then in terms of the lead Poisson, the Hamiltonian is what is also considered, that is its energy. Thank you very much.
Thank you so much. Let's have a Q&A session. That's great. Well, I see that your method's smarter particle is able to reduce the number of particles like 5 times before that. Was it 1B, 1B? 1B. What if you extend that to 2B or 3B, 3B?
So when you look at the structure for 2D, it's the same thing. It's going to be smarter, get more variables. Automatically, if it's 2D, 3D, the variables the standard PIC will also increase because each P will have, maybe if it's 2, P1, P2, and what it will increase. The same applies to ours. But in terms of the advantage, in our preliminary results, we are still doing better as compared to, we're still saving space and then additional as compared to standard chemical.
Do you expect that saving will increase as you go higher dimensional?
Yes.
All right, we have a question from Junchia Wang. He asked, thank you, Mandela. It's a great talk for particle in cell simulation. Sometimes you have to split and merge those macro particles during the splitting and merging process. Does this scheme also satisfy the conservation of energy momentum charges and mass?
Yes, it does. Because in what we did, and what the work that we are building on, what happens is there is a pullback. So as they split, there's a way that the ideal in the S is able to end up having that pullback, and that will help us to make sure the Hamiltonian is conserved, and hence the energy is also conserved. Yes. Because the whole idea here is that we wanted it to energy conserved. So the splitting and the merging, the hybridization that we are working with is able to conserve that.
Well, thank you. Is there any other questions? Yes. Petros, you wanna unmute Petros and then ask?
Okay. Hi. I was wondering if you had, I wrote it down, but I was wondering if you had any nonlinear examples to show. It's all very well and good to show two extremely elementary linear problems and claim with great chest pumping that one is conserving energy, but energy conservation or structure conservation is challenged with nonlinear problems only. So do you have any examples of two stream with finite temperature, low enough and close enough beams where you have chaotic evolution, and just exactly how much of that do you preserve with your low order moment schemes?
Yeah, so that's the next work that we are working on. So this one is our first paper that we realize that it's working. And the nonlinear examples, even for nonlinear London damping and etc., we have worked on it. We realized that in our preliminary results, it's how do you call it? It's showing good results over there as well. So I'm sure in our subsequent paper we're able to get that one shown. But the structure is preserving. It's working for that one. So based on the result that we have.
I asked about the two stream. Nonlinear Lana damping is a steady state solution. So again, it's trivial. The question is, have you looked at non-trivial problems such as two stream instability run long enough that it'll become highly nonlinear, way past the linear growth rate phase?
Oh, okay, no, we have not done that. It's a good question, then I'll note it and then maybe work on it here.
Thank you.
Okay, sounds good. Next question is by Jen. Jen, would you unmute yourself and ask your question directly?
Oh, yeah, hi. In the talk, you were referring to particle in cell, like standard particle in cell, but only you considered Dirac delta functions for them. But modern particle in cell methods typically have B-splines or shape functions of particles. So it's not really just a simple particle, but some smooth function to reduce that numerical heating and also reduce that noise, similarly to your method. So have you compared your method to particle in cell codes with B-spline?
Yes. So this particular standard, the one that we just showed here, is using a piecewise linear function in terms of how they do the interpolation. When the shape function there is piecewise linear, because they don't really use the delta function to get it done. But the goal here is after we get our 2D working, we now want to compare it with future problems to be able to see how maybe like well-known example, not well-known codes available like simile and what have you, VPIC and what have you, to see how it performs. But this one is using piecewise linear. The standard PIC here, we use piecewise linear, not just the delta function. We approximated it by using delta and piecewise linear. Yes.
Okay, well, thank you. Next question is by Andrew. Andrew, if you want to unmute and ask directly.
Hi. So my question is, like, have you looked at the error in other quantities such as like the charge density or number density and or the distribution function itself?
Okay, so for distribution function, I have not, but the other quantities we have looked at it and comparably. The only thing is, as the particle, so if we go below 20,000, the error, our error will start fading. If you go below 20,000, you realize earlier, then we go back. So
You're not sharing. You're not sharing.
oh, okay. Yeah, so there are issues. So when you go beyond this, when you compare the exact solution of our charge density as compared to the one with standard PIC, our results now, that's where the error is not as good. So basically, just with elementary understanding, realize that you can only reduce the particles to a particular kind of limitation. There's a limit you can reduce the particles up to. Beyond that limit, the method will not be working as much as you want it to work. Yes. In terms of distribution function, we try doing it, but it's basically a bit technical because it looks like we're comparing apples to oranges. Because we'll need to make sure we have all our 4 variables at a particular time to see what happens at that particular time with the standard PIC. And there's a bit of work that we have to do there, but we didn't do the F. But in terms of energy, here we are looking at energy. By energy, in terms of Hamiltonian, in terms of charge density, compared to our one, and it works well. Yes.
Okay, thank you. Petros, do you want to unmute again?
You always ask me after I type it all up. Okay. Okay, so I was wondering if your code is designed to or happens to have only been used as one in which all these moments that you keep evolve are the same number of moments for all the particles, independently of where the particle happens to be in velocity space.
I didn't get the question.
Petros, can you repeat?
Okay, you didn't hear, or should I use different language? What was the problem?
I didn't hear.
Oh, okay. Well, stop me if you don't hear me again.
Okay.
The same thing doesn't happen everywhere in phase space in a physics simulation of an interesting problem. For instance, if you have Landau damping, there's a particular phase velocity at which the wave is born and lives. And that happens to be, because of the neutron plasma wave, something like 3 or 4 V thermal. Okay, so natural units at velocities of 3 or 4, which is very far in the tail of the Maxwellian distribution function, right?
Yes, yes.
Okay, so do you treat those particles any differently than you treat the bulk particles or ones with even higher velocity? What is the velocity space localized information that you're using before using words like smart particle? The first thing particles know is where they are in velocity space. Is your method smart enough to know that?
Yes.
How?
It does.
How is it different? How does it use different moments depending on where it is in velocity space? I didn't see anything on your slides about that, or maybe I missed it.
So, in the kind of how the decomposition is done. So the reason why you don't see, remember, when I was in our first toy problem, the reason why here, this is where the moment is, right? When L is one or when L is greater than 2, you then have this, and this is where we have our standard, the standard PIC particles. So when you are dealing with this side, that's where you need to now keep track properly of how our velocity and then our velocity in terms of the phase space is what is moving. So in this example, we are not tracking this at all here. But in the next work that we are doing, definitely you need to handle the two tails properly to make sure it's aligned properly with what. And that's why I said earlier, K means look good here, but we will need maybe a better clustering mechanism to deal with it when we are now moving beyond L equals 0 and 1.
I think you're saying that you're more focused on the Hamiltonian aspects and space reduction and this sort of thing, a la Weinstein, and that has nothing to do with the sampling part, which is a separate thing. Is that what you're saying?
Yes.
Okay, I would say that if you combine the two, then you can use words like smart.
Sure. Okay.
All right. Well, thank you. I think it's time's up. Time to wrap up. 7 after 11. Yeah. So let's thank our speaker Mandela for the nice talk and wonderful Q&A sessions. And thank you all also who participated in this nice special seminar we hosted.
Thank you.
At the last moment.
Thank you.
Well, thank you again. All right.